Alright, this is Pierre Miller, bringing you with another Bandicam tutorial on how to make your own DIY nuclear fission reactor. The requirements: you need a vacuum chamber, preferably in a spherical shape, a roughing vacuum pump capable of reaching at least 75 microns vacuum, a secondary high vacuum pump, either a turbo pump or oil diffusion pump, a high voltage supply, preferably capable of at least 40 kilovolts, 10 megaamps, must be negative polarity, a high voltage divider probe for use with a digital multimeter, a thermocouple or baratron of appropriate scale, vacuum gauge, a neutron radiation detector, either a proportional HE3 or BF3 tube with counting instrumentation or bubble dosimeter, a Geiger counter, preferably a scintillator type for X-ray detection and for your own personal safety. Deuterium gas, which can be purchased out of gas or extracted from D20 through electrolysis. It is much easier and more effective to use compressed gas. You also need a large ballast resistor in the range of 50 to 100K and at least a foot long. You need a camera and a TV display for viewing the inside of the reactor. You need lead to shield the camera viewport, and general engineering tools. A machine shop, if at all possible, although 90% of mine was built with nothing but a Dremel and cordless drill. The only thing you can't really build without a shop is scratching building the vacuum chamber, honestly. And that's it for the requirements. Not much, probably get it at your local Walmart, maybe. Step 1, need to assemble the vacuum chamber. A quality high vacuum chamber is required for the fuser to operate. Sometimes an appropriate chamber can be found on eBay, but generally it is best to make one yourself. Parts can be scourged for $100 or purchased new for $500. Personally, I would do the used, but whatever. Get 2 stainless steel hemispheres. Purchase 2 corresponding conflat flanges, 8 flanges in my case. Bore out holes for accessory flanges, and then TIG weld it all together. Flanges are typically either of the KF or the conflat style. Conflat can be seen in the image below as flanges with bolts, and KV quink flange are seen as those with only jambs holding an O-ring on the mating surface. My bad. Only weld on the inside, never on the outside. Do not do this, okay? Since virtual leaks can be formed and both inside and outside are welded. If you've never TIG welded before, it would be wise to have someone with experience do it, as the welds must be flawless with no pin-sized holes or porous areas to hold a vacuum. After machining thoroughly clean the chamber and avoid getting fingerprints in it, since these will outgas, which means that vacuum pressure molecules in the oil of fingerprints or machining oil will become vapor and make it hard to maintain plasma stability or reach a good ultimate vacuum level. Now that's it for step 1. Step 2. Prepare high vacuum pump. Install the oil diffusion pump or a turbo pump if you have a bit of luck scourging or a higher budget. Fill the pump with quality diffusion pump oil to whatever Fill the pump with quality diffusion pump oil to whatever fill level the pump documentation suggests. Attach the inlet to a valve, which then connects to the chamber, see diagram, and attach the outlet to a mechanical backing pump capable of reaching at least around 75 microns. Any higher and the diffusion pump will not operate properly or the oil will oxidize quickly. Make sure the pump is sufficiently cooled. Many oil diffusion pumps require water cooling. Smaller ones, such as the one pictured, can get by with a decent airflow. Once this is assembled, turn on the mechanical pump and wait for the vacuum to reach at least 75 microns. Next, you can test the high vacuum pump by turning on the boiler on the diffusion pump. After it warms up, could take a while, the vacuum should rapidly drop below the single micron range. Now, step 3, build Inner grid. The inner grid, where the high voltage is applied, must now be built and attached to a high voltage feed-through. It is best to use a metal such as tungsten for the grid wires since it is a very high melting point and their grid will get extremely hot during high power runs. This can be built however you wish, as long as it resembles a spherical shape of roughly 1 to 1.5 inches in diameter. For a 6 to 8 inch chamber, it should work fine. The grid should be internally attached to an electrical feed-through such as the one pictured in the second image. This feed-through needs to be at least rated for the cathode voltage that will be used. Typically 40 kilovolts is a good target voltage. Step 5. Oh shit. Wait. Fuck. Step 4 isn't needed. Step 5. High voltage. If you can purchase a power supply, occasionally but not commonly found surplus, appropriate for fission use, the high voltage becomes very simple. Simply take the output of the 40 kilovolt negative supply and attach it to the chamber with a physically large high voltage 50 to 100K OMH ballast resistor in series, large enough that its length will not flash over if 40 kV is applied to a plasma runaway or arc discharge. Everybody knows this. You should also know this. This is common sense. The difficulty is that it's too often difficult, if not impossible, to find an appropriate, fully assembled DC supply of this voltage level that is affordable to the amateur scientist. You are an amateur scientist. This is talking about you. Pictured is my high-frequency ferrite transformer pair with a 4-stage multiplier seen behind it. That's mine, by the way. If a fully assembled power supply, typically manufactured by either Gassman or Spellman, there are a few options. 1. Find an X-ray transformer, and if necessary, either reverse the reticures for negative polarity, or add reticures if it has none. An X-ray transformer core won't have reticures. It probably will if it's in its oil tank. Or 2. Build a switching high-frequency ferrite power supply. This is what I did. However, it requires a bit of EE experience, since several aspects must be resonant, and if it is ever taken out of tune, the transistors will burn out. Probably not the best option for people with little electrical background. Step 6. Set up neutron detection. This is a big one here, guys. You better pay attention. The proof of fusion and a quantitative analysis of how much fusion is obtained through detecting neutron radiation, the byproduct of DD fusion reaction. There are 3 options which can be described. They are in order of descending ease and setup. First, we have a neutron bubble dosimeter. A bubble dosimeter is a small unit with a gel in it that forms bubbles when ionized by neutron radiation. This is the easiest form of neutron detection available, since all you have to do is unscrew the top and set it to the next fusor. Some of the drawbacks are that it is an integrated detector, which means you have to get in a total neutron emission number over time as it was used, rather than any instances neutron rate. Additionally, they are somewhat hard to get, since the only company to make them is BubbleTech in Canada, which has a minimum order of 3 with steep shipping and handling. Expect to at least spend $700 if ordering directly from them and not in a group buy. Additionally, they tend to be fairly worn out after a year of shelf life, although I've kept mine in a refrigerated storage container at 50 degrees Fahrenheit, and it seems to be like new after after more than a year. The advantage is that its calibration data is provided with purchase, and of course it is easy. Second way, we have silver activation. When silver is placed near the reactor with a moderator, peripheral water, hope, etc., between it and the neutron source, since only thermal neutrons will activate the material, it becomes slightly radioactive with decent neutron figures. It has a short half-life of only a few minutes, but if you quickly put a Geiger counter next to the silver, counts can be detected. In my best runs, I have gotten a piece of silver to about 250 CPM over background on a CDV 700 Geiger counter. The disadvantages of this are that it requires a decent neutron flux, at least about 100,000 neutrons, which is above the average beginner's first run neutron rate. Also, it is somewhat difficult to calibrate, and the counts cannot be taken until after the